Welcome to a journey through the true scale of the Milky Way. Over the next 2 hours, we will explore the almost incomprehensible size of our home galaxy, the vast distances between stars, and the cosmic measurements that challenge our ability to understand just how big our galaxy really is. Whether you're here to fall asleep, to study, or simply to let your mind drift through the enormity of space, take a deep breath, settle in, and prepare to have your sense of scale forever changed. The Milky Way is big. This is something we all know intellectually. But knowing something and truly understanding it are two very different things. When we say the Milky Way is 100,000 light years across, we're using numbers that sound simple, 100,000. But what does that really mean? A light year is the distance light travels in 1 year. Light moves at 300,000 kilometers per second. In 1 second, light travels far enough to circle the Earth 7.5 times. In 1 year, light travels nearly 10 trillion kilometers. And the Milky Way is 100,000 of these light years across. To put it another way, if you could travel at the speed of light, the fastest speed possible in the universe, according to Einstein's theory of relativity, it would take you 100,000 years to cross the Milky Way from one edge to the other. 100,000 years. That is longer than all of recorded human history. That is longer than modern humans have existed as a species. And yet, despite this almost unimaginable size, the Milky Way is just one galaxy among hundreds of billions in the observable universe. It is not particularly large. It is not particularly small. It is average, ordinary. One galaxy among countless others, each separated from its neighbours by millions of light years of empty space. But for us, the Milky Way is everything. It is our home. It is the only galaxy we can study in detail, the only galaxy where we can see individual stars, measure distances precisely, and map structures with accuracy. It is our cosmic address, our island in the infinite ocean of space. Let's begin our gentle journey through the true scale of the Milky Way and discover just how vast, how magnificent, and how humbling our home galaxy really is. Before we can truly understand the scale of the Milky Way, we must first understand the measurement we use to describe cosmic distances. That measurement is the light year, and the light year is based on the speed of light, the fastest thing in the universe. Light travels at 299,792 kilometers per second. For simplicity, we usually round this to 300,000 kilometers per second. This speed is absolute. It is the cosmic speed limit. Nothing can travel faster than light. Not matter, not energy, not information. Light speed is the ultimate barrier, written into the fabric of space-time itself by the laws of physics. At this speed, light can circle the Earth's equator 7.5 times in a single second. Think about that for a moment. In the time it takes you to blink, light has travelled around the entire planet multiple times. In 1 second, light travels from the Earth to the Moon and back with time to spare. The Moon is about 384,000 kilometers away, and light covers that distance in just over 1 second. In 1 minute, light travels 18 million kilometers. This is about half the distance from the Earth to the Sun. The Sun is approximately 150 million kilometers from Earth, and light from the Sun takes 8 minutes and 20 seconds to reach us. This means that when you look at the Sun, you are seeing it as it was 8 minutes ago. You are looking into the past. In 1 hour, light travels more than 1 billion kilometers. This is enough to travel from the Sun past the orbit of Jupiter. In 1 day, light travels 26 billion kilometers, enough to reach beyond the orbit of Neptune and out into the Kuiper Belt, the region of icy bodies beyond the planets. And in 1 year, light travels 9.46 trillion kilometers. This is 1 light year. It is the standard unit of measurement for interstellar distances, the distances between stars. To put this in perspective, let's compare it to something familiar. The fastest spacecraft ever built by humans is the Parker Solar Probe, which reached a maximum speed of 192 kilometers per second as it dove close to the Sun. This is incredibly fast by human standards, faster than anything we have ever created. But compared to light, it is crawling. At this speed, the Parker Solar Probe would take more than 158,000 years to travel 1 light year. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object. It is travelling at about 17 kilometers per second relative to the Sun. It has been travelling for more than 45 years, and it is now about 23 billion kilometers from Earth. This sounds like an enormous distance, and it is. But in light years, Voyager 1 has travelled only about 0.0025 light years. It has barely left the solar system. At its current speed, Voyager 1 would take more than 17,000 years to travel just 1 light year. This is the challenge of interstellar travel. The distances are so vast, and even our fastest spacecraft are so slow that crossing even the smallest interstellar distances would take thousands of years with current technology. The stars are not just far away. They are almost unreachably far away. But light crosses these distances effortlessly. Light from the nearest star to our Sun, Proxima Centauri, takes 4.24 years to reach us. This star is 4.24 light years away. When we look at Proxima Centauri, we are seeing it as it was 4.24 years ago. We are looking across space and time simultaneously. The light year is more than just a unit of distance. It is also a measure of time. Every light year we look outward into space is also a year we look backward in time. When we observe a star 100 light years away, we see it as it was 100 years ago. When we observe a galaxy 1 million light years away, we see it as it was 1 million years ago, long before humans existed. This property of light, travelling at a finite speed, means that astronomy is a form of time travel. We cannot travel to the past, but we can observe the past by looking at distant objects. The farther we look, the farther back in time we see. This is one of the most profound insights of modern astronomy. The universe has a history, and we can observe that history by looking at objects at different distances. In the Milky Way, the distances between stars are measured in light years. The nearest stars to our Sun are a few light years away. Most stars in our region of the galaxy are dozens or hundreds of light years away. The centre of the galaxy is about 26,000 light years away, and the far edge of the galaxy is about 65,000 light years away from us. These distances are almost impossible to visualize. Our brains did not evolve to comprehend such scales. We understand meters and kilometers because those are the scales of our daily lives, but light years are beyond our intuition. We can calculate with them, we can reason about them, but we cannot truly see them in our mind's eye. And yet, these are the distances we must work with to understand the Milky Way. The galaxy is so large that light, the fastest thing in the universe, takes 100,000 years to cross it. This is the true scale of the Milky Way, and we have only just begun to explore it. The light year is our window into cosmic scale. It is the first step in understanding just how vast the universe really is, and once we grasp the light year, once we begin to appreciate what it means for light to travel for years or centuries or millennia before reaching our eyes, we can begin to understand the true enormity of the Milky Way. Every photon of light that enters your eye from a distant star has been travelling through space for years, decades, or centuries. It has crossed the vast emptiness between the stars, unchanged and undisturbed, carrying information about the star that emitted it. When you look up at the night sky, you are not seeing the stars as they are now. You are seeing them as they were when that light began its journey. You are seeing the past preserved in light, spread across the sky. The light year is the key to understanding cosmic time and cosmic distance, and it is the foundation upon which all our measurements of the Milky Way are built. Now that we understand the light year, let us use it to explore our cosmic neighbourhood. Let us look at the nearest stars to our Sun, and begin to appreciate the distances that separate even close neighbours in the galaxy. The nearest star to our Sun is Proxima Centauri. a small red dwarf star that is part of the Alpha Centauri star system. Proxima Centauri is 4.24 light-years away. This means that light from Proxima Centauri takes 4.24 years to reach Earth. When we look at Proxima Centauri tonight, we are seeing it as it was 4.24 years ago. 4.24 light-years is about 40 trillion kilometers. To put this in perspective, if the Sun were the size of a basketball and you placed it in New York City, then Proxima Centauri on the same scale would be another basketball placed in Tokyo. The distance between them would be about 11,000 kilometers, roughly the distance from New York to Tokyo. And the space between them would be almost entirely empty. This is the nature of the galaxy. The stars are like tiny islands in a vast ocean of emptiness. They're separated by distances so large that light takes years to cross them. Even the nearest stars are almost incomprehensibly far away. If we wanted to send a spacecraft to Proxima Centauri with current technology, it would take tens of thousands of years. The Voyager 1 spacecraft, travelling at 17 kilometers per second, would take more than 73,000 years to reach Proxima Centauri. A human lifetime is not nearly enough. 1,000 human lifetimes would not be enough. The journey would span hundreds of generations. But Proxima Centauri is not alone. It is part of a triple star system called Alpha Centauri. The other two stars in the system, Alpha Centauri A and Alpha Centauri B, are slightly farther from us, at about 4.37 light-years. These two stars orbit each other, and Proxima Centauri orbits the pair at a great distance. Alpha Centauri A is similar to our Sun, a yellow star with about the same size and temperature. Alpha Centauri B is slightly smaller and cooler, an orange star. Together they form a binary system, two stars locked in a gravitational dance, orbiting their common centre of mass every 80 years. Recent observations have revealed that Proxima Centauri has at least two planets. One of them, Proxima Centauri B, orbits in the star's habitable zone, the region where liquid water could exist on the surface of a planet. This makes Proxima Centauri B one of the nearest potentially habitable planets to Earth. It is our closest exoplanetary neighbour, a world just 4.24 light-years away. But even though Proxima Centauri is our nearest stellar neighbour, we know relatively little about it. It is too faint to see with the naked eye. You need a telescope to observe it, and studying its planets in detail is extraordinarily difficult. We can detect them through their gravitational effects on the star, but imaging them directly, seeing what they actually look like, is beyond our current capabilities. Beyond Alpha Centauri, the next nearest star is Barnard's star, a red dwarf located 6.0 light-years away. Barnard's star is moving through space very quickly relative to the Sun. It is approaching us, and in about 10,000 years it will be the closest star to our Sun, overtaking Proxima Centauri. Barnard's star is small and dim, with only about 16% of the Sun's mass. It is very old, probably around 10 billion years old, more than twice the age of the Sun. It is also known to have at least one planet, a super-Earth orbiting close to the star. At 6 light-years, Barnard's star is 50% farther from us than Proxima Centauri. This may not sound like much, but in absolute terms, it is an additional 20 trillion kilometers. The distances add up quickly when we measure in light-years. The next nearest stars form a pair called Lumen 16, a binary system of brown dwarfs located 6.5 light-years away. Brown dwarfs are objects that are more massive than planets, but not massive enough to sustain hydrogen fusion like true stars. They glow faintly with infrared light from the heat of their formation, slowly cooling over billions of years. Lumen 16 was discovered only in 2013, despite being one of our nearest neighbours. This shows how difficult it is to find faint objects, even when they are relatively close. Within 10 light-years of the Sun, there are only about a dozen star systems. Most of them are red dwarfs, small dim stars that make up the majority of stars in the galaxy. There are no giant stars, no brilliant blue supergiants, no spectacular nebulae. Our neighbourhood is quiet. populated mostly by faint, long-lived red dwarfs that will continue burning for trillions of years. This is typical of the galaxy. Most stars are small and dim. The bright stars we see in the night sky are not nearby. They are distant but powerful, massive stars that shine so brightly they are visible across hundreds or thousands of light years. The nearest stars are too faint to see without a telescope. Within 20 light years, there are about 100 star systems. Within 50 light years, there are about 2,000. Within 100 light years, there are about 14,000. The number grows rapidly as we expand our sphere of observation, but even at 100 light years, we are still in the immediate neighbourhood of the Sun, a tiny fraction of the galaxy's total size. 100 light years is 1/10 of the diameter of the Milky Way. It is a drop in the cosmic ocean, and yet it contains thousands of stars, many of them with planets, some of those planets potentially habitable. The galaxy is not just vast. It is also extraordinarily populous, but the distances between stars, even neighbouring stars, are so great that they might as well be isolated islands. Stars do not interact with each other in any meaningful way unless they are very close, within a fraction of a light year. Most stars live their entire lives without ever coming close to another star. They are born, they shine for billions or trillions of years, and they die, all in isolation. Our Sun will probably never have a close encounter with another star. The distances are too great, and the stars are too small compared to the space between them. The galaxy is not crowded. It is almost entirely empty space, with tiny pinpoints of light scattered throughout. This is the scale of our neighbourhood. Stars separated by light years, dozens of trillions of kilometres. Distances so vast that light, the fastest thing in the universe, takes years to cross them. And this is just the beginning. We have not even left our immediate surroundings. The true scale of the Milky Way is far, far larger. Let us now expand our view. We have seen the nearest stars, the immediate neighbourhood within a few dozen light years. Now let us zoom out and look at the structure of the Milky Way as a whole. Let us look at the disk. The Milky Way is a disk galaxy. Most of its stars are arranged in a flat rotating disk like a cosmic frisbee. This disk is about 100,000 light years in diameter, but only about 1,000 light years thick in most places. Near the centre, it thickens to a few thousand light years, but in the outer regions it is very thin. To visualise this, imagine a dinner plate. The plate is 100 units across, but only 1 unit thick. This is roughly the proportions of the Milky Way's disk. It is extremely flat compared to its diameter. Our Sun is located in this disk, about 26,000 light years from the centre. We are roughly halfway out from the centre to the edge. We are in a region called the Orion Spur, a minor spiral arm that branches off from one of the major arms. The disk contains most of the galaxy's visible matter. Hundreds of billions of stars orbit the Galactic Center, all moving in roughly the same direction, creating the overall rotation of the galaxy. The Sun, along with all the stars in our neighbourhood, orbits the centre of the galaxy at about 230 kilometers per second. Even at this tremendous speed, it takes the Sun about 230 million years to complete one orbit around the galaxy. This period is called a galactic year. Since the Sun formed about 4.6 billion years ago, it has completed only about 20 orbits around the galaxy. 20 trips around the Galactic Center in the entire history of the Sun. This gives you a sense of the immense scale of the galaxy. Even travelling at hundreds of kilometers per second, it takes hundreds of millions of years to go around once. The disk is not uniform. It is divided into several spiral arms, regions where stars and gas are more densely concentrated. These arms are not solid structures, they are density waves, regions where stars slow down and bunch together as they orbit the galaxy, like cars slowing down in a traffic jam. The arms themselves rotate around the galaxy at a different speed than the stars, and stars pass through the arms as they orbit. The major spiral arms of the Milky Way are called the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. Each arm stretches for thousands of light years, curving gracefully around the galaxy. These arms are where most of the galaxy's star formation occurs. They are bright with the light of young, hot stars and glowing nebulae. Between the arms, the disk is darker and quieter. There are still stars there, but they are older, cooler, and less luminous. The interarm regions are more peaceful, less subject to the disruptions and violence of active star formation. The disk also contains vast amounts of gas and dust, the raw material for future star formation. This gas is mostly hydrogen, the simplest and most abundant element in the universe. It is very thin, with only a few atoms per cubic centimetre, but spread across the enormous volume of the disk, it adds up to billions of solar masses of material. This gas is concentrated in the spiral arms, where it is compressed by density waves and triggered to collapse and form new stars. In the interarm regions, the gas is more diffuse, spread out in a thin layer above and below the plane of the disk. The dust is made of tiny solid particles, mostly carbon and silicates, created in the atmospheres of dying stars and scattered into space. These dust grains are incredibly small, typically less than 1 micrometer across, smaller than bacteria. But there are so many of them that they block and scatter starlight, creating the dark lanes we see in images of the Milky Way. The dust absorbs visible light but allows infrared light to pass through. This means that to see through the dust and observe the structure of the galaxy, we must use infrared telescopes. Infrared light penetrates the dust, revealing the hidden stars and structures beneath. The thickness of the disk, about 1,000 light-years, is still an enormous distance. If you could stand on one face of the disk and look through it to the other side, you would be looking through 1,000 light-years of stars, gas, and dust. Light from stars on the far side of the disk would be dimmed and reddened by the dust, but it would still reach you, carrying information about those distant stars. The disk is where most of the action happens in the galaxy. This is where stars are born, where they live and where they die. This is where planetary systems form, where life might arise, where civilizations might evolve. The disk is the living, dynamic part of the galaxy. Above and below the disk, at distances of several thousand light-years, there is the halo, a spherical region containing old stars and globular clusters. But the halo is sparse, with far fewer stars than the disk. The disk is where the galaxy's mass and energy are concentrated. The rotation of the disk is one of its defining features. Every star, every cloud of gas, every grain of dust orbits the Galactic Center, held in place by gravity. The inner regions rotate faster, completing an orbit in less time. The outer regions rotate more slowly, but the overall pattern is one of rotation. A vast whirlpool of stars and gas spinning around the central black hole. This rotation is what gives the galaxy its stability. Without rotation, the stars would fall inward toward the center, pulled by gravity. But the rotation provides an outward centrifugal force that balances gravity, keeping the stars in stable orbits. The disk is in dynamic equilibrium, a balance between inward gravitational pull and outward rotational motion. The disk of the Milky Way is a structure of almost unimaginable size, 100,000 light-years across, 1,000 light-years thick, containing hundreds of billions of stars, rotating once every few 100 million years. It is a cosmic structure, vast and majestic, and we are a part of it. We are embedded in the disk, one star among hundreds of billions, orbiting the center along with all the others, and yet the disk is only part of the galaxy. There is more to the Milky Way than the disk. There is the bulge, the halo, the dark matter halo, and the satellites. Each component adds to the total size and mass of the galaxy. The disk is just the most visible part, the part that shines brightest, the part we notice first when we look at images of spiral galaxies. But to truly understand the scale of the Milky Way, we must look at all its components, and we must measure distances not in kilometers, not in millions of kilometers, but in light years, tens of thousands of light years, distances that light takes millennia to cross. At the very centre of the Milky Way, 26,000 light-years from Earth, lies the heart of the galaxy. This is the Galactic Center, a region of incredible density, intense radiation, and exotic phenomena. And at the very core of this region sits a supermassive black hole, 26,000 light-years. Let us pause and consider this distance. It is about 246 trillion kilometers. If you could travel at the speed of light, it would take you 26,000 years to reach the galactic center. If you could travel at the speed of the fastest spacecraft humans have ever built, it would take you more than 4 million years. The galactic center is not just far away, it is hidden. Between us and the center, there are thick clouds of dust that block visible light. When we look toward the constellation Sagittarius, where the galactic center lies, we see only a faint glow, obscured by dark lanes of dust. We cannot see the center with optical telescopes, but we can see it in other wavelengths. Infrared light penetrates the dust, revealing the dense clusters of stars near the center. Radio waves pass through the dust effortlessly, allowing us to map the structure of the gas and the magnetic fields. X-rays reveal the hot, energetic processes happening near the black hole. Using these techniques, astronomers have built up a detailed picture of the galactic center, even though we cannot see it directly with our eyes. The central region of the galaxy, within a few thousand light-years of the center, is called the bulge. The bulge is a roughly spherical concentration of old stars, much denser than the disk. In the bulge, stars are packed much more closely together than in our neighborhood. If you lived on a planet in the bulge, your night sky would be filled with thousands of stars brighter than Venus, and there would be no true darkness at night. But the bulge itself is only the outer part of the central region. At the very heart of the galaxy, within a few light-years of the center, there is a region of even greater density called the nuclear star cluster. This cluster contains millions of stars packed into a tiny volume, orbiting the supermassive black hole at the center. The black hole is called Sagittarius A star, usually written as SGR-AE. It has a mass of about 4 million times the mass of the Sun. This is enormous, but in terms of physical size, the black hole itself is surprisingly small. The event horizon, the boundary beyond which nothing can escape, has a diameter of only about 44 million kilometers, roughly the size of Mercury's orbit around the Sun. But the influence of the black hole extends far beyond the event horizon. Stars within a few light-years of the black hole are dominated by its gravity. They orbit at incredible speeds, some completing an orbit in just a few decades. One of these stars, called S2, has been observed for more than 20 years as it orbits Sagittarius A star. S2 is a massive blue star, about 15 times the mass of the Sun. It orbits the black hole on a highly elliptical path, coming as close as 18 light-hours from the black hole at its closest approach. At this distance, the star is moving at about 5,000 kilometers per second, nearly 2% of the speed of light. Observations of S2 have allowed astronomers to test Einstein's theory of general relativity in the extreme gravitational environment near the black hole. The orbit of S2 behaves exactly as general relativity predicts, with effects like gravitational redshift and orbital precession clearly visible in the data. The distance to the galactic center, 26,000 light-years, has been measured with increasing precision over the years. Early estimates in the 20th century range from 20,000 to 30,000 light-years. But with modern techniques, including observations of stars orbiting Sagittarius A star and measurements of the distances to star clusters in the bulge, the distance is now known to be about 26,000 light-years, with an uncertainty of only a few hundred light-years. This distance places us about halfway out from the center to the edge of the galaxy. We're in a relatively quiet region, far from the intense radiation and crowded conditions of the galactic center, but not so far out that we're in the sparse outer regions of the disk. 26,000 light-years also means that when we observe the galactic center, we are seeing it as it was 26,000 years ago. The light we receive today left the galactic center when the Earth was in the last ice age, when woolly mammoths roamed the planet and early humans were just beginning to create art and culture. If an astronomer at the Galactic Center were observing the sun right now, they would be seeing the sun as it was 26,000 years ago, long before recorded human history. They would not see our cities, our spacecraft, our radio signals. They would see a star with no obvious signs of technological civilization, because those signs have not yet had time to reach them. This is the nature of cosmic distances. Not only are things far away in space, they are also far away in time. The farther we look, the farther back in time we see. Every observation is an observation of the past. The Galactic Center is also a region of intense activity. Although the black hole is currently quiet, not actively feeding on large amounts of matter, there is evidence of past outbursts. The Fermi bubbles, two enormous lobes of high-energy gas extending above and below the galactic plane, are thought to have been created by a massive burst of energy from Sagittarius A star millions of years ago. The Galactic Center is also home to strong magnetic fields, high-energy cosmic rays, and intense stellar winds from massive stars. It is a hostile environment where radiation levels would be lethal to any life as we know it. And yet, it is also a fascinating laboratory for studying extreme physics, where gravity, magnetism, and radiation reach levels we can barely comprehend. The distance to the Galactic Center, 26,000 light-years, is one of the fundamental measurements in astronomy. It sets the scale for the entire galaxy. Once we know how far away the center is, we can use it to calibrate other distance measurements and build up a complete picture of the galaxy's structure. And it reminds us once again of the true scale of the Milky Way. We are 26,000 light-years from the center. Light, traveling at the fastest speed in the universe, takes 26,000 years to cross that distance. The galaxy is not just big, it is almost incomprehensibly vast, a structure on a scale that dwarfs anything in our everyday experience. The disk of the Milky Way is not smooth and uniform. It is divided into several spiral arms, vast structures that curve around the galaxy like the arms of a cosmic pinwheel. These arms are among the most visually striking features of spiral galaxies, and they are also among the most important for understanding how galaxies work. The spiral arms of the Milky Way are enormous. Each arm stretches for thousands of light-years, curving gracefully around the galactic center. The Perseus arm, one of the major arms, extends for more than 20,000 light-years. The Sagittarius arm, where our Sun is located in a minor branch called the Orion Spur, is similarly vast. These distances are difficult to comprehend. 20,000 light-years is about 200 quintillion kilometers. If you could drive a car at highway speeds, it would take you more than 200 trillion years to travel the length of one spiral arm. The arms are structures on a truly cosmic scale. The spiral arms are not solid objects, they are density waves, regions where stars and gas are temporarily more concentrated. As stars orbit the galaxy, they pass through the spiral arms, slowing down and speeding up in response to the gravitational forces from the denser regions. The arms themselves rotate at a different speed than the stars, creating a pattern that persists even though individual stars are constantly moving through it. Imagine a traffic jam on a highway. The jam itself stays in roughly the same place, even though individual cars move through it. The cars slow down as they enter the jam, then speed up as they leave it. The spiral arms work in a similar way. Stars slow down as they enter an arm, increasing the density, then speed up as they leave, maintaining the spiral pattern. The spiral arms are where most of the galaxy's star formation occurs. As gas clouds pass through an arm, they are compressed by the density wave. This compression can trigger the collapse of the cloud, leading to the formation of new stars. The arms are therefore bright with the light of young, hot stars and glowing nebula where stars are currently forming. These young stars are massive and luminous, shining with intense blue and ultraviolet light. They are also short-lived, burning through their fuel in just a few million years before exploding as supernovae. This means that the spiral arms are constantly being refreshed with new stars, maintaining their brightness over time. The spiral arms are also dangerous places. The high density of stars and gas means that collisions and close encounters are more common. Supernova explosions are frequent, bathing the surrounding region in intense radiation. If a planet were located in the dense part of a spiral arm, it would be exposed to much higher levels of cosmic rays and gamma rays than a planet in a quieter region like our own. Our Sun is located in the Orion Spur, a minor arm or spur that branches off from the Sagittarius arm. We are between the major arms, in a relatively quiet region. This may be one of the reasons life was able to develop on Earth. We are shielded from the worst of the radiation and disruption that occurs in the major arms, but even in our relatively quiet location, we are not entirely safe. Every 200 million years or so, as the Sun orbits the galaxy, we pass through one of the major spiral arms. During these passages, the risk of nearby supernova and other disruptive events increases. Some scientists have speculated that these passages might be linked to mass extinction events on Earth, though the evidence is still uncertain. The spiral arms are also regions of intense beauty. In images of spiral galaxies taken by telescopes like Hubble, the arms glow with vibrant colours: blue from young stars, red and pink from glowing hydrogen gas, dark lanes from dust clouds. The arms are where the galaxy is most alive, most dynamic, most visually spectacular. But the scale of the arms is difficult to appreciate from images. When we look at a picture of a spiral galaxy, we are seeing the entire galaxy compressed into a single image. The arms look close together, almost touching in some places. But in reality, the distance between spiral arms is thousands of light years. The space between the arms is vast, filled with older stars and diffuse gas. The width of a single spiral arm is about 3,000 to 5,000 light years. This means that if you were travelling through the galaxy at the speed of light, it would take you several thousand years just to cross a single arm. And the distance between arms is even greater, 10,000 light years or more. This is the scale we're dealing with. Structures that take light thousands of years to cross. Distances that are almost impossible to visualize. And yet, these are the building blocks of the galaxy, the fundamental structures that give the Milky Way its shape and character. The spiral arms also play a crucial role in the evolution of the galaxy. They regulate star formation, concentrating it in specific regions and times. They mix the interstellar medium, spreading heavy elements created by dying stars throughout the galaxy. And they create the beautiful patterns we see when we look at spiral galaxies, patterns that are not just aesthetically pleasing but also scientifically meaningful. Understanding the spiral arms requires sophisticated computer simulations. Astronomers create models of the galaxy, simulating the orbits of millions of stars and the behaviour of gas clouds under gravity. These simulations show how density waves can form and persist over billions of years, creating the spiral pattern. But there are still mysteries. We do not fully understand what creates the density waves in the first place. We do not know why some galaxies have tightly wound spirals while others have more open patterns. We do not know how the spiral pattern evolves over time, or how long it can persist before being disrupted. The Milky Way's spiral arms are among its most prominent features. They are vast, beautiful, and scientifically important. They are structures on a scale that challenges our comprehension, stretching for thousands upon thousands of light years, containing billions of stars and vast clouds of gas and dust. And they remind us once again of the true scale of the galaxy. We're embedded in one small part of one minor spur, and yet the structures around us extend for thousands of light years in every direction. The galaxy is not just large, it is almost inconceivably vast. We have talked about the diameter of the Milky Way, 100,000 light years from edge to edge. But the galaxy is not a sphere, it is a disk, flat and thin compared to its width. And the thickness of this disk is another important part of understanding the galaxy's scale. The disk of the Milky Way is about 1,000 light years thick in most places. Near the centre, it thickens to several thousand light years. In the outer regions, it thins to only a few hundred light-years, but on average the disk is about 1,000 light-years thick. 1,000 light-years, this is still an enormous distance. It is about 9.5 trillion kilometers. Light takes 1,000 years to cross the thickness of the disk, and yet, compared to the diameter of the disk, 100,000 light-years, the thickness is tiny. The disk is 100 times wider than it is thick. To visualize this, imagine a sheet of paper. A standard sheet of paper is about 28 centimeters long and 21 centimeters wide, with a thickness of about 0.1 millimeters. The ratio of width to thickness is about 2,000 to 1. The Milky Way's disk has a ratio of about 100 to 1, so it is proportionally thicker than a sheet of paper, but it is still extremely flat. This flatness is a result of rotation. When the galaxy formed, billions of years ago, it started as a roughly spherical cloud of gas. As the cloud collapsed under its own gravity, it began to rotate. The rotation created a centrifugal force that resisted collapse in the plane, perpendicular to the axis of rotation. But in the direction of the rotation axis, there was no centrifugal force to resist collapse. As a result, the cloud collapsed into a disk. The stars and gas settled into a thin plane, all orbiting in roughly the same direction. This is why the Milky Way is flat. It is a natural consequence of rotation and gravity. But the disk is not perfectly flat. Stars in the disk have some motion perpendicular to the plane, moving up and down in what is called the vertical direction. This vertical motion causes stars to oscillate above and below the plane as they orbit the galaxy. Our Sun, for example, is currently about 70 light-years above the galactic plane, and it is moving upward. Over the next few million years, it will reach a maximum height of about 250 light-years above the plane, then fall back down, passing through the plane and reaching a maximum depth of about 250 light-years below the plane. This oscillation takes about 70 million years to complete, and the Sun has gone through this cycle dozens of times since it formed. This vertical motion is common to all stars in the disk. The result is that the disk has a finite thickness, determined by the typical vertical velocities of stars. Young stars, recently formed in the plane of the disk, have small vertical velocities and stay close to the plane. Older stars have larger vertical velocities, acquired through gravitational interactions with other stars and with giant molecular clouds, and they oscillate farther from the plane. This means that the disk is not uniform in thickness. Near the plane, where young stars are concentrated, the disk is thin, only a few hundred light-years thick. But if you include all the stars, including the old stars that oscillate far from the plane, the disk is thicker, up to 1,000 light-years or more. The gas in the disk is even more concentrated toward the plane than the stars. The gas is very thin, only about 100 to 200 light-years thick. This is because gas clouds collide with each other, and these collisions dissipate energy, causing the gas to settle closer to the plane. Stars, on the other hand, do not collide, so they retain their vertical motion indefinitely. The thickness of the disk has important implications for star formation and for the environment in which stars like the Sun live. If you are near the plane, you are in a region of active star formation, with young stars, glowing nebulae, and frequent supernova explosions. If you are far from the plane, you are in a quieter region, with older stars and less activity. Our Sun, being about 70 light-years above the plane, is in a relatively quiet region. We are not in the most active part of the disk, where star formation is most intense. This may have been beneficial for the development of life on Earth. A more active environment might have exposed the Earth to more radiation and disruption. The vertical structure of the disk also affects our view of the Milky Way. When we look toward the galactic plane, we are looking through the thin dimension of the disk, through only about 1,000 light-years of stars and gas. When we look perpendicular to the plane, we are looking out of the disk, and we can see farther into intergalactic space without obstruction. This is why the Milky Way appears as a band across the sky. We are looking along the plane of the disk, seeing the combined light of billions of stars all along our line of sight. When we look in other directions, away from the plane, we see fewer stars and more distant galaxies. The thickness of the disk, 1,000 light-years, is still an enormous distance. If you could travel at the speed of light, it would take you 1,000 years to cross from one face of the disk to the other. If you could travel at the speed of a spacecraft, it would take you hundreds of thousands of years. And yet this enormous distance is small compared to the width of the disk. The galaxy is extremely flat, a cosmic pancake, a disk of stars and gas spinning through space. This flatness is one of its defining characteristics, a direct result of its rotation, and a key to understanding its structure and evolution. The thickness of the disk also determines how we observe the galaxy. From our position inside the disk, we have a difficult time seeing the overall structure. We can see the disk edge on as a band of light across the sky, but we cannot easily see the spiral arms or the overall shape. We are like ants crawling on the surface of a plate, able to see the edge but not able to step back and see the whole plate from above. To understand the structure of the Milky Way, we must use indirect methods. We measure the distances and velocities of stars and gas clouds, and we use these measurements to build up a three-dimensional map of the galaxy. We observe other spiral galaxies, similar to the Milky Way, and we use them as templates to understand what our own galaxy might look like from the outside. But the fundamental challenge remains. We are embedded in the galaxy, and the galaxy is so large that we cannot easily see its structure. The thickness of the disk, though small compared to its width, is still 1,000 light-years, and that is more than enough to obscure our view. The flatness of the Milky Way is a beautiful example of the interplay between rotation and gravity, two of the fundamental forces that shape the universe, and the thickness of the disk, 1,000 light-years, is another reminder of the true scale of the galaxy. Even the thin dimension of the disk is vast beyond comprehension. Surrounding the flat disk of the Milky Way, extending far above and below the plane, is a vast spherical region called the halo. The halo contains old stars and globular clusters, the ancient relics of the galaxy's formation. And it is here, in the halo, that we begin to appreciate the true three-dimensional scale of the Milky Way. The halo extends to distances of at least 100,000 light-years from the Galactic Center, roughly the same as the diameter of the disk. But while the disk is flat, the halo is spherical, surrounding the galaxy in 3 dimensions. This means the volume of the halo is much larger than the volume of the disk. The stars in the halo are very different from the stars in the disk. They are old, more than 10 billion years old, formed in the first billion years after the Big Bang. They are metal poor, containing only trace amounts of elements heavier than hydrogen and helium. And they orbit the galaxy on long elliptical paths that take them far above and below the disk. The halo is sparsely populated. While the disk contains hundreds of billions of stars, the halo contains only about 1% of the galaxy's stellar mass. The stars in the halo are spread over an enormous volume, making the halo a quiet, empty region compared to the crowded disk. But despite its sparse population, the halo is important for understanding the galaxy. The halo stars are fossil records of the galaxy's early history. By studying their chemical compositions and motions, astronomers can learn about the conditions in the early universe and the formation of the first galaxies. The halo also contains globular clusters, dense spherical collections of hundreds of thousands of stars. Globular clusters are among the oldest objects in the galaxy, with ages ranging from 10 to 13 billion years. They orbit the galaxy on long, slow paths, passing through the disk every few hundred million years. There are about 150 to 200 known globular clusters in the Milky Way. They are scattered throughout the halo, some close to the Galactic Center, others far out in the outer halo. The most distant globular cluster, called NGC 2419, is about 300,000 light-years from the Galactic Center, 3 times the diameter of the disk, 300,000 light-years. This is an almost unimaginable distance. Light takes 300,000 years to travel from NGC 2419 to the Galactic Center. If an astronomer in NGC 2419 were observing the Milky Way right now, they would be seeing it as it was 300,000 years ago, long before modern humans existed. NGC 2419 is so distant that it is sometimes called the intergalactic wanderer. For many years, astronomers debated whether it was even part of the Milky Way or a separate small galaxy. But observations have confirmed that it is gravitationally bound to the Milky Way, orbiting the galaxy on a very long elliptical path. The halo is also home to stellar streams, long ribbons of stars that wrap around the galaxy. These streams are the remnants of smaller galaxies and globular clusters that were torn apart by the Milky Way's gravity. As these objects fell toward the galaxy, tidal forces stretched them out into long lines of stars. The Sagittarius stream, one of the most prominent, wraps around the Milky Way multiple times, like thread wound around a ball. The stream contains millions of stars, all that remains of the Sagittarius dwarf elliptical galaxy, a small galaxy that is currently being devoured by the Milky Way. These streams extend for hundreds of thousands of light years, tracing the orbits of the disrupted objects. They are direct evidence that the Milky Way grew by consuming smaller galaxies, a process that has been going on for billions of years and continues today. The halo is also where the dark matter halo resides. The dark matter halo is even more extended than the stellar halo, reaching out to distances of several 100,000 light years, possibly even 1,000,000 light years or more. The dark matter halo contains most of the galaxy's mass, far more than all the stars and gas combined. This dark matter is invisible. It does not emit light, it does not absorb light, it does not interact with ordinary matter except through gravity. But we know it is there because of its gravitational effects on the stars and gas in the galaxy. Without the dark matter halo, the galaxy would not hold together. The scale of the halo is truly cosmic. We're talking about distances of 100,000 to 300,000 light years, distances so vast that light takes hundreds of thousands of years to cross them. The halo is not crowded like the disk. It is almost empty, with stars and clusters scattered like islands in a vast ocean. But the halo is essential to the structure and evolution of the galaxy. It is the fossil record of the galaxy's past. It is the reservoir of ancient stars and the graveyard of consumed galaxies, and it is the domain of dark matter, the invisible scaffolding that holds the entire galaxy together. When we think of the Milky Way, we often think of the disk, the flat plane of stars and spiral arms that we see in images. But the halo is just as important, and in terms of volume, much larger. The halo extends the scale of the galaxy from 2 dimensions to 3, surrounding the disk in a vast sphere that reaches out into the depths of space. The halo is a reminder that the Milky Way is not just a disk. It is a complex 3-dimensional structure with components at many different distances and scales. And each component adds to our understanding of how big the galaxy really is. Where does the Milky Way end? This is a more difficult question than it might seem. Galaxies do not have sharp edges. They fade gradually into the surrounding space, becoming dimmer and more diffuse until they merge imperceptibly with the intergalactic medium. The disk of the Milky Way, as we have said, is about 100,000 light years in diameter. But this is measured to the point where the density of stars drops to some arbitrary threshold. If we choose a different threshold, we get a different size. There is no clear boundary where the galaxy ends. The same is true for the halo. The stellar halo extends to at least 100,000 light years, but there are stars and star clusters even farther out. The globular cluster, NGC 2419, as we mentioned, is 300,000 light years from the centre. Is it part of the galaxy? Most astronomers say yes because it is gravitationally bound and orbits the Galactic Center, but it is far beyond what we usually think of as the edge of the galaxy. The dark matter halo is even more extended. Computer simulations suggest that the dark matter halo of the Milky Way extends to distances of several 100,000 light years, possibly even 1,000,000 light years. This is the virial radius of the galaxy, the point at which the galaxy's gravity is no longer strong enough to hold material in orbit. 1,000,000 light years. This is 10 times the diameter of the visible disk. If the dark matter halo extends this far, then the Milky Way is truly enormous, a structure that dwarfs the visible galaxy. But even defining the dark matter halo is tricky. The halo does not have a sharp edge. It fades gradually, blending into the dark matter halos of neighbouring galaxies. The Milky Way and the Andromeda Galaxy, for example, are about 2.5 million light-years apart, but their dark matter halos may already be touching or overlapping. In a sense, galaxies are not isolated objects. They are part of a larger cosmic web of dark matter, connected by invisible filaments that stretch across millions of light-years. The boundaries between galaxies are fuzzy and ill-defined, but for practical purposes, we can say that the Milky Way extends to at least 100,000 light-years in the disk and the stellar halo, and possibly several 100,000 light-years or more if we include the dark matter halo. These are the scales we're dealing with. 100,000 light-years is about 950 trillion kilometers. If you could travel at the speed of light, starting from one edge of the galaxy, it would take you 100,000 years to reach the other edge. 100,000 years is longer than modern humans have existed as a species. It is longer than recorded history. It is longer than agriculture, longer than cities, longer than any human civilization. And yet, this is just the diameter of one galaxy. There are hundreds of billions of galaxies in the observable universe, each separated from its neighbours by millions of light-years. The Milky Way, vast as it is just one small part of a much larger cosmos. The edge of the galaxy is also where we find some of the galaxy's satellite galaxies. The Magellanic Clouds, the two largest satellites, are about 160,000 and 200,000 light-years away, just beyond the main disk. These galaxies are gravitationally bound to the Milky Way, orbiting it on long paths that will eventually bring them closer and lead to their destruction. There are dozens of smaller satellite galaxies orbiting the Milky Way, most of them dwarf galaxies containing only a few million stars. These satellites are scattered throughout the halo, some close, some far, all held in orbit by the gravity of the Milky Way. The most distant known satellite galaxy is called Crater 2, a dwarf galaxy located about 380,000 light-years from the Galactic Center. Crater 2 is very faint, only discovered in 2016. Despite being one of the largest satellite galaxies by size, it is so diffuse, with its stars spread over such a large area, that it is almost invisible. 380,000 light-years. This is farther than the diameter of the visible Milky Way, and yet Crater 2 is still considered part of the Milky Way system because it is gravitationally bound and orbiting the galaxy. The edge of the galaxy is not a sharp boundary. It is a gradual fading, a transition from the dense star-filled regions of the disk and bulge to the sparse, empty regions of the outer halo and intergalactic space. And depending on how you define edge, the galaxy could be 100,000 light-years across, or 300,000, or even 1,000,000. But no matter how you define it, the scale is enormous. We are talking about distances that light takes hundreds of thousands of years to cross, distances that are almost impossible to visualize, almost impossible to comprehend, and this is just one galaxy. The Milky Way is not unique. It is not special. It is an average spiral galaxy, one of billions in the universe. There are galaxies much larger than the Milky Way, and galaxies much smaller. There are elliptical galaxies, irregular galaxies, dwarf galaxies, and giant galaxies. The universe is filled with galaxies, each one a vast collection of stars, gas, and dark matter, each one separated from its neighbours by millions of light-years. The edge of the Milky Way is the edge of our cosmic home. Beyond it lies intergalactic space, the vast emptiness between galaxies, and eventually other galaxies, other collections of stars, other potential homes for life and intelligence. But within the Milky Way, within this 100,000 light-year span, there are hundreds of billions of stars, many of them with planets, some of those planets potentially habitable. The galaxy is not just big, it is also extraordinarily rich, filled with countless worlds, countless opportunities for complexity and perhaps for life. The edge of the galaxy is where the Milky Way fades into the cosmos. But it is not an end. It is a transition, a blending of one structure into the larger universe beyond. We have talked about distances, the diameter of the disk, the thickness of the disk, the extent of the halo. But to truly appreciate the scale of the Milky Way, we must think about volume. How much space does the galaxy actually occupy? The volume of a structure is the three-dimensional space it fills. For a sphere, the volume is 4/3 pi times the radius cubed. For a disk, the calculation is more complex, but we can approximate it by treating the disk as a cylinder and the halo as a sphere. The disk of the Milky Way, as we've said, is about 100,000 light-years in diameter and 1,000 light-years thick. Treating it as a cylinder, the volume is pi times the radius squared times the height. The radius is 50,000 light-years, so the volume is approximately pi times 50,000 squared times 1,000, which is about 7.8 billion cubic light-years. 7.8 billion cubic light-years. This is an almost incomprehensible number. A cubic light-year is the volume of a cube 1 light-year on each side. 1 cubic light-year is about 850 trillion cubic kilometers, so the disk of the Milky Way has a volume of about 7.8 billion times 850 trillion cubic kilometers, which is about 6.6 sextillion cubic kilometers. That is 6,600,000 cubic kilometers. To put this in perspective, the entire solar system out to the orbit of Neptune, a sphere about 9 billion kilometers across, has a volume of about 3 trillion cubic kilometers. The disk of the Milky Way is about 2 million times larger in volume than the solar system, and the disk is only part of the galaxy. The halo, extending to 100,000 light-years in all directions from the center, can be approximated as a sphere with a radius of 100,000 light-years. The volume of this sphere is 4/3 pi times 100,000 cubed, which is about 4 trillion cubic light-years. 4 trillion cubic light-years. This is about 500 times larger than the volume of the disk. The halo, though it contains far fewer stars, occupies far more space. If we include the dark matter halo, extending to several 100,000 light-years, the volume becomes even larger. A sphere with a radius of 500,000 light-years has a volume of about 500 trillion cubic light-years, more than 100,000 times the volume of the disk. These numbers are so large that they lose meaning. Our brains cannot visualize volumes of trillions of cubic light-years. We can write the numbers, we can do the calculations, but we cannot truly comprehend what they represent. But perhaps we can gain some sense of scale by thinking about density. How much stuff is there in this enormous volume? The disk contains about 200 to 400 billion stars. Let's say 300 billion, a reasonable middle estimate. These stars are spread over a volume of about 8 billion cubic light-years. This gives an average density of about 38 stars per cubic light-year. But even this density is misleading, because stars are not evenly distributed. Most of the stars are concentrated near the galactic plane and within the spiral arms. In these regions, the density is much higher, perhaps hundreds of stars per cubic light-year. In the spaces between spiral arms and far from the plane, the density is much lower. In our neighborhood, the density is about 0.15 stars per cubic light-year. This means that on average, stars are separated by about 2 light-years. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away, which is somewhat farther than average, but not unusual. This means that most of the volume of the disk is empty space. The stars, though numerous, are tiny compared to the distances between them. If you were travelling through the galaxy, you would spend almost all your time in empty space, with stars appearing as isolated pinpoints of light in the distance. the halo is even more sparse. The stellar halo contains about 1% of the galaxy's stars, about 3 billion stars, spread over a volume of 4 trillion cubic light-years. This gives an average density of about 0.00075 stars per cubic light-year, or about 1 star per 1,300 cubic light-years. In the halo, stars are incredibly isolated. The nearest neighbour to a typical halo star might be dozens or hundreds of light-years away. If you lived on a planet orbiting a halo star, your night sky would be almost empty, with only a handful of faint stars visible to the naked eye. The dark matter halo is even more diffuse. Although it contains most of the galaxy's mass, it is spread over an enormous volume. The average density of dark matter in the solar neighbourhood is about 0.3 protons per cubic centimetre. This is incredibly tenuous, far less dense than the best laboratory vacuums on Earth. And yet, integrated over the entire volume of the dark matter halo, this adds up to trillions of solar masses, far more mass than all the stars in the galaxy combined. The galaxy, despite containing hundreds of billions of stars, is mostly empty space. The volume is enormous, but the matter within it is spread very thin. This is true of the universe as a whole. Space is vast and matter is rare. The universe is not crowded. It is almost entirely empty. But the emptiness is part of what makes the galaxy so vast. If the stars were packed more closely together, the galaxy would be smaller. The enormous distances between stars are what give the galaxy its immense size. The volume of the Milky Way, whether we measure it as billions of cubic light-years or sextillions of cubic kilometers, is a number that defies intuition. We cannot visualize it. We cannot hold it in our minds. But we can appreciate in an abstract way that the galaxy is not just big in 1 dimension or 2, it is big in 3 dimensions. It is a vast 3-dimensional structure, filled mostly with emptiness, but also with hundreds of billions of stars and vast clouds of gas and dust. This is the scale of the Milky Way, not just a diameter of 100,000 light-years, but a volume of trillions of cubic light-years, an expanse of space so large that light takes hundreds of thousands of years to cross it, a structure so vast that it contains hundreds of billions of stars and yet remains mostly empty. Let us now think about what it would mean to travel across the Milky Way. We have talked about the size of the galaxy in abstract terms, in light-years and cubic light-years, but what would it actually be like to travel these distances? The fastest speed possible, according to Einstein's theory of relativity, is the speed of light. Nothing with mass can reach this speed, but light itself travels at 300,000 kilometers per second, and in principle, if we could somehow travel at this speed, we could cross the galaxy in 100,000 years. 100,000 years. This is an unimaginably long time by human standards. Modern humans, Homo sapiens, have existed for about 300,000 years. All of recorded human history, from the first written records to the present day, spans only about 5,000 years. 100,000 years is 20 times longer than all of human civilization. If a spacecraft left Earth today, travelling at the speed of light, and crossed the Milky Way to the far edge, it would arrive 100,000 years from now. In that time, entire civilizations could rise and fall, languages would evolve and disappear, continents would shift, ice ages would come and go, humanity, if it still exists, would be utterly transformed. But we cannot travel at the speed of light. We are made of matter, and matter cannot reach light speed. The fastest we can travel, with current technology, is a tiny fraction of light speed. The Voyager 1 spacecraft, launched in 1977, is currently the fastest and most distant human-made object. It is travelling at about 17 kilometers per second relative to the Sun. At this speed, Voyager 1 would take about 1.7 million years to travel just 1 light year. To cross the galaxy, at 100,000 light years, would take about 170 billion years. 170 billion years. This is more than 10 times the current age of the universe. It is an incomprehensible span of time. Stars would live and die, galaxies would collide and merge, the universe itself would evolve beyond recognition, and Voyager would still be making its way across the Milky Way. Even with more advanced propulsion systems, the journey would be extraordinarily long. Suppose we could build a spacecraft that travels at 1% of the speed of light, about 3,000 kilometers per second. This is far beyond our current capabilities, but it is at least theoretically possible with technologies like nuclear pulse propulsion or antimatter engines. At 1% of light speed, crossing the galaxy would take 10 million years. This is still an impossibly long time. 10 million years ago, the ancestors of humans and chimpanzees had just diverged. 10 million years in the future, humanity as we know it would almost certainly not exist, evolved into something unrecognizable or extinct. At 10% of light speed, the journey would take 1 million years. At 50% of light speed, 500,000 years. Even at 99% of light speed, it would take about 100,000 years, accounting for the effects of relativity. No matter how we calculate it, crossing the Milky Way is a journey that spans geological timescales far longer than any human life, any human civilization, perhaps even any species. This is the reality of interstellar travel on galactic scales. The distances are so vast that even travelling at relativistic speeds, close to the speed of light, the journey would take longer than human history. Travelling to the nearest stars might be possible within a human lifetime if we can achieve high enough speeds. But travelling across the entire galaxy is beyond the scope of any reasonable planning horizon. But let us imagine for a moment that we could somehow make this journey. What would we see along the way? Leaving Earth, we would pass through the solar system in a matter of hours or days, depending on our speed. The Moon, Mars, the asteroid belt, Jupiter, Saturn, all would flash by as we accelerated outward. Within a few years, we would leave the solar system entirely and enter interstellar space. For the next few years or decades, depending on our speed, we would travel through the space between stars. This space is not entirely empty. It contains very thin gas, a few atoms per cubic centimetre and tiny grains of dust, but it is essentially a vacuum, far more perfect than any vacuum we can create in a laboratory. Eventually, after years of travel, we would approach another star. If we passed close enough, we might see planets orbiting it, rocky worlds or gas giants, each with their own unique characteristics. We might see moons, rings, asteroid belts. We might even see signs of life, though this would be extraordinarily rare. Then we would continue on, leaving that star system behind, entering the space between stars once again. And this pattern would repeat over and over thousands of times as we made our way across the galaxy. Star after star, each one unique, each one separated from its neighbours by years of travel time. As we travelled farther from Earth, the sun would fade, becoming just another star among many, then a faint point of light, then indistinguishable from the background. We would lose all contact with Earth. Radio signals travelling at the speed of light would take years or centuries to reach us, and by the time we received them, they would be describing events long past. We would be truly alone, travelling through the vastness of space, with no hope of return, no hope of communication, nothing but the stars ahead and the darkness around us. After thousands of years, we might pass through a spiral arm. The density of stars would increase, and we might see giant clouds of gas and dust, glowing nebulae where new stars are forming. The sky would be brighter, filled with more stars, some of them massive and brilliant, shining with intense blue light. After tens of thousands of years, we might approach the Galactic Center. The density of stars would increase dramatically, and the sky would be filled with millions of stars brighter than Venus, creating a perpetual twilight. We would pass close to the supermassive black hole, though at a safe distance, and we would see the intense radiation and high-energy processes happening there. Then we would continue on, crossing to the other side of the galaxy, passing through more spiral arms, more regions of star formation, more empty spaces between stars. After 100,000 years, we would finally reach the far edge of the galaxy, emerging into intergalactic space, the vast emptiness between galaxies. Looking back, we would see the Milky Way as a whole, a spiral galaxy seen from the outside, a beautiful structure of light and darkness, a cosmic whirlpool spinning slowly through the void, and ahead, in the distance, other galaxies, each one a collection of billions of stars, each one separated from the Milky Way by millions of light years. This is what it would mean to cross the Milky Way, a journey of 100,000 years at the speed of light, longer than human history, longer than human existence. A journey through hundreds of billions of stars, through nebulae and black holes, through spiral arms and empty spaces. A journey from one edge of our cosmic home to the other, from one side of the galaxy to the other. It is a journey we will almost certainly never make, but imagining it helps us appreciate the true scale of the Milky Way. The galaxy is not just big, it is vast beyond comprehension. A structure so large that crossing it would take longer than civilization, longer than our species, longer than we can meaningfully imagine. We have explored the size of the Milky Way, the distances across the disk and through the halo. But size is only one measure of scale. To truly understand the magnitude of the galaxy, we must also consider its mass. How much matter does the Milky Way contain? The total mass of the Milky Way is difficult to measure precisely. We cannot simply add up all the stars because much of the galaxy's mass is invisible. Dark matter makes up the majority of the mass, and we can only infer its presence through gravitational effects. Current estimates suggest that the total mass of the Milky Way, including all stars, gas, dust, and dark matter, is about 1 trillion to 1.5 trillion times the mass of our Sun. This is written as 1 to 1.5 times 10 to the 12th solar masses, 1 trillion solar masses. Let us pause and consider what this means. The Sun is already incredibly massive. It contains 99.86% of all the mass in our solar system. The Sun's mass is about 330,000 times the mass of Earth, and the Milky Way contains 1 trillion times this mass. If we tried to write out the mass of the Milky Way in kilograms, we would need a number with about 42 digits. It is roughly 2 quintillion kilograms, a number so large it becomes meaningless. But not all of this mass is in stars. In fact, most of it is not. The stars, all 300 billion or so of them, contain only about 10 to 20% of the galaxy's total mass. That is about 100 to 200 billion solar masses in stars. The gas and dust, the raw material for future star formation, contains another few percent of the mass, about 10 to 20 billion solar masses. This gas is mostly hydrogen, spread throughout the disk in vast clouds and diffuse regions. The rest of the mass, about 80 to 85%, is dark matter. This means that about 800 billion to 1 trillion solar masses of the Milky Way is invisible, detectable only through its gravitational effects. This dark matter forms a vast halo surrounding the visible galaxy. It extends far beyond the stars, reaching out to distances of several 100,000 light-years or more. The dark matter halo is what holds the galaxy together, providing the gravitational pull that keeps stars in their orbits. Without dark matter, the stars in the outer regions of the galaxy would be moving too fast to remain bound. They would escape the galaxy's gravity and fly off into intergalactic space. But they do not escape. They remain in orbit, held in place by the gravity of the dark matter halo. The mass of the Milky Way has been measured through several methods. One method is to observe the motions of stars and gas in the galaxy. By measuring how fast they are moving and how they are distributed, astronomers can calculate the total mass needed to produce the observed motions. Another method is to observe the motions of satellite galaxies orbiting the Milky Way. The satellite galaxies are held in orbit by the Milky Way's gravity, and by measuring their orbits, we can calculate the total mass of the Milky Way. A third method is to look at the gravitational effects of the Milky Way on its surroundings. The Milky Way and the Andromeda Galaxy are approaching each other, pull together by their mutual gravity. By measuring the speed of this approach and modelling the gravitational interaction, astronomers can estimate the masses of both galaxies. All of these methods give roughly consistent results. The Milky Way has a total mass of about 1 trillion to 1.5 trillion solar masses, with significant uncertainty. This makes the Milky Way a fairly typical large spiral galaxy. It is not the most massive galaxy known, but it is far from the smallest. It is a heavyweight in the cosmic arena, though not a champion. To put this in perspective, the Andromeda Galaxy, our nearest large galactic neighbour, is estimated to have a mass of about 1.5 trillion solar masses, slightly more massive than the Milky Way. The two galaxies are comparable in size and mass, which is why their eventual collision will be such a dramatic event. Smaller dwarf galaxies like the Large Magellanic Cloud have masses of only about 10 billion solar masses, 100 times less than the Milky Way. Giant elliptical galaxies, on the other hand, can have masses of 10 trillion solar masses or more, 10 times greater than the Milky Way. The mass of the galaxy also determines its gravitational influence. The Milky Way's gravity extends far beyond the visible galaxy, affecting objects hundreds of thousands of light years away. Satellite galaxies, high-velocity clouds, and even intergalactic gas are all influenced by the Milky Way's gravity. This gravitational influence defines the Milky Way's sphere of influence, the region of space where its gravity is dominant. Within this sphere, objects are bound to the Milky Way and orbit it. Outside this sphere, objects are free, either moving independently through intergalactic space or bound to other galaxies. The mass of the Milky Way is not static, it is growing over time. The galaxy is constantly consuming smaller satellite galaxies, adding their mass to its own. The Sagittarius dwarf elliptical galaxy, for example, is currently being torn apart and absorbed by the Milky Way. Over the next few billion years, its stars will be scattered throughout the Milky Way's halo, and its mass will be added to the galaxy's total. The Milky Way is also accreting gas from the intergalactic medium. High-velocity clouds fall onto the galactic disk, bringing fresh material that can form new stars. This infall of gas is essential for sustaining star formation over billions of years. In about 4 billion years, the Milky Way will merge with the Andromeda Galaxy, creating a new, larger galaxy with a combined mass of about 2.5 to 3 trillion solar masses. This merged galaxy, sometimes called Milkomeda, will be one of the dominant galaxies in the local group. The mass of the Milky Way, 1 trillion solar masses, is a measure of its gravitational dominance, its ability to hold stars and gas in orbit, to capture and consume smaller galaxies, and to shape the space around it. It is a measure of the galaxy's power, its presence in the cosmic arena. And like the size of the galaxy, the mass is almost incomprehensible, 1 trillion times the mass of the Sun, a number with 42 digits when written in kilograms, a quantity of matter so vast that it bends space and time, creating a gravitational well that holds hundreds of billions of stars in its grip. The mass of the Milky Way is another dimension of its scale. Not just how big it is, but how much stuff it contains, and the answer is an almost unimaginable amount. The Milky Way contains hundreds of billions of stars. This number, often stated casually, is worth contemplating. Hundreds of billions, between 200 billion and 400 billion depending on the estimate. Let us say 300 billion as a reasonable middle value. 300 billion stars. This is more than 40 stars for every person alive on Earth today. It is more stars than there are grains of sand on a beach. It is more stars than the number of seconds in 10,000 years. If you tried to count the stars in the Milky Way, counting 1 star per second, 24 hours a day, without stopping, it would take you more than 9,000 years to count them all. Longer than recorded human history, longer than civilization itself, and each of these stars is a sun, a massive sphere of plasma generating energy through nuclear fusion, shining with its own light. Each star has a history, a life cycle that spans millions or billions of years. Many of these stars have planets. Some of those planets might harbour life. The stars of the Milky Way are not all the same. They come in a vast range of sizes, masses, temperatures, and colours. The smallest stars, red dwarfs, have masses as low as 8% of the Sun's mass. They are cool, dim, and incredibly long-lived, burning their fuel so slowly that they can shine for trillions of years. Red dwarfs are the most common type of star in the galaxy. About 70 to 80% of all stars are red dwarfs. This means that of the 300 billion stars in the Milky Way, about 220 billion are red dwarfs. Despite being so numerous, red dwarfs contribute relatively little to the total light of the galaxy because each one is so dim. The next most common type of star is stars like our Sun, yellow dwarf stars with masses similar to the Sun. These stars make up about 7 to 8% of the galaxy's stellar population, about 20 to 25 billion stars. They are more luminous than red dwarfs, and they have lifetimes of about 10 billion years, long enough for planets around them to potentially develop complex life. Larger stars with masses greater than the Sun are less common. Stars with masses 2 to 8 times the Sun's mass, called intermediate mass stars, make up a few percent of the population. Stars with masses greater than 8 times the Sun's mass, called massive stars, are rare, making up less than 1% of all stars. But these massive stars are incredibly important. Despite being rare, they are so luminous that they contribute a significant fraction of the galaxy's total light. A single massive star can be as bright as 100,000 or 1 million suns. These stars are the brilliant blue and white giants we see in star-forming regions, the stars that light up nebulae and create the beautiful images we associate with space. Massive stars also have short lives. A star with 20 times the Sun's mass might live only 10 million years before exhausting its fuel and exploding as a supernova. This is only 1,000th the lifetime of the Sun. In the time the Sun has been shining, about 4.6 billion years, 460 generations of massive stars have lived and died. The most massive stars in the Milky Way, with masses up to 200 times the Sun's mass, live only a few million years. These stars are incredibly rare, perhaps only a few thousand in the entire galaxy at any given time, but they are also incredibly influential, producing powerful stellar winds that shape their surroundings and eventually exploding as supernovae that enrich the galaxy with heavy elements. The Milky Way also contains many stars that have already died. White dwarfs, the remnants of stars like the Sun, are very common. There are an estimated 10 billion white dwarfs in the galaxy, slowly cooling over billions of years. Neutron stars, the remnants of massive stars, are less common, with an estimated 100 million in the galaxy. And black holes, the most extreme stellar remnants, number perhaps 10 million to 100 million, scattered throughout the galaxy. The distribution of stars in the galaxy is not uniform. Most stars are concentrated in the disk, especially in the spiral arms. The Galactic Center has an extremely high density of stars, with millions of stars packed into a region only a few light years across. The halo, in contrast, is very sparse, with stars separated by dozens or hundreds of light years. In our neighbourhood, about 26,000 light years from the Galactic Center, the density is about 0.15 stars per cubic light year. This means that on average, each star has a sphere of about 2 light years radius to itself, with the nearest neighbour typically a few light years away. But this average hides a lot of variation. Some stars are in dense clusters, with neighbours less than a light year away. Other stars are isolated, with no neighbours for dozens of light years. Our Sun is in a relatively typical region, not particularly dense and not particularly sparse. The stellar population of the Milky Way is constantly changing. New stars are born at a rate of about 1 to 3 stars per year. This might not sound like much, but over billions of years, it adds up. In the last billion years, 1 to 3 billion new stars have been born in the Milky Way. At the same time, stars are dying. Low-mass stars live for trillions of years, so none of them have died yet in the 13.8 billion year history of the universe. but intermediate mass and massive stars die relatively quickly. The rate of stellar death roughly matches the rate of stellar birth, keeping the total stellar population roughly constant over time. 300 billion stars, each one a world unto itself, each one potentially with planets, moons, asteroids, comets, each one a possible home for life, for intelligence, for civilizations we cannot imagine. If only one star in a million has a planet with intelligent life, that would still be 300,000 civilizations in the Milky Way. If only one in a billion, that would still be 300 civilizations. We do not know the true number. We have not yet detected any signs of extraterrestrial intelligence, but the sheer number of stars suggests that we are probably not alone. The stellar population of the Milky Way is a vast community, a collection of suns spread across 100,000 light years, each one shining with its own light, each one following its own path through space, each one a part of the grand structure we call our galaxy. 300 billion stars. It is a number almost too large to comprehend, but it is real. The Milky Way is not just big in terms of size and mass. It is also big in terms of population. It is a city of stars, a metropolis of suns, a cosmic community on a scale that dwarfs anything on Earth. If the Milky Way contains 300 billion stars, how many planets does it contain? This is a question that astronomers have only recently been able to answer with any confidence. Until the 1990s, we knew of only 9 planets, the 8 planets of our solar system, plus Pluto, which was considered a planet at the time. But in the last 30 years, thanks to missions like Kepler and TESS, and to ground-based surveys, we have discovered thousands of planets orbiting other stars. These exoplanets have revealed that planets are not rare, they are common. Nearly every star has at least one planet, and many stars have multiple planets. Based on current data, astronomers estimate that there is at least one planet per star in the Milky Way on average. This means the galaxy contains at least 300 billion planets. Some estimates are even higher, suggesting there might be as many as 1 trillion planets in the galaxy. 1 trillion planets. This is more than the number of stars. It is a vast population of worlds, each one unique, each one with its own characteristics, its own geology, its own history. These planets come in a wide variety of types. There are gas giants like Jupiter, massive worlds made mostly of hydrogen and helium, with no solid surface. There are ice giants like Neptune, with thick atmospheres of hydrogen, helium and methane, surrounding cores of rock and ice. There are rocky planets like Earth and Mars, with solid surfaces and thin atmospheres. And there are types of planets we do not have in our solar system, like super-Earths and mini-Neptunes, planets intermediate in size between Earth and Neptune. The diversity of exoplanets has been one of the great surprises of the last few decades. We have found planets orbiting very close to their stars, completing an orbit in just a few days. These hot Jupiters are gas giants heated to thousands of degrees by their nearby stars. We have found planets in highly elliptical orbits, experiencing extreme variations in temperature and radiation. We have found planets in binary star systems, orbiting 2 stars at once. We have also found planets in the habitable zone, the region around a star where temperatures are right for liquid water to exist on the surface. Water is essential for life as we know it, so planets in the habitable zone are of particular interest in the search for extraterrestrial life. How many habitable planets are there in the Milky Way? This depends on how we define habitable. If we require a rocky planet in the habitable zone of a sun-like star, the number might be a few billion. If we expand the definition to include planets around red dwarfs, which are much more common, the number could be tens of billions. One recent estimate suggests there could be as many as 40 billion Earth-sized planets in the habitable zones of their stars in the Milky Way. 40 billion potentially habitable worlds. This is a staggering number, a vast arena for life to arise and evolve. But habitable does not mean inhabited. A planet in the habitable zone might have no water, or a toxic atmosphere, or intense radiation from stellar flares. It might be geologically dead, with no volcanism or plate tectonics to recycle nutrients. It might be tidally locked, with one side always facing the star and the other in perpetual darkness. We do not yet know how common life is in the universe. We have only one example: Earth. We do not know if life is a common outcome of planetary evolution or a rare fluke that requires extraordinary circumstances. We do not know if intelligent life is common or rare. We do not know if technological civilizations are abundant or vanishingly scarce. But the sheer number of planets in the Milky Way suggests that the opportunities for life are vast. If even a tiny fraction of those 40 billion potentially habitable planets actually harbour life, the galaxy could be teeming with living worlds. And many of these planets might be very different from Earth. Life might exist in the subsurface oceans of ice-covered moons, like Europa or Enceladus in our own solar system. Life might exist in the atmospheres of gas giants, floating in clouds of water vapour. Life might exist on rogue planets, worlds ejected from their star systems and drifting through interstellar space, heated by internal radioactivity rather than by a sun. The scale of planetary systems in the Milky Way is staggering. 300 billion stars, at least 300 billion planets, possibly a trillion, tens of billions of potentially habitable worlds. It is a vast cosmic landscape filled with countless worlds we will probably never see, never visit, never know. Each planet is a world with its own mountains and valleys, its own atmosphere and weather, its own history stretching back billions of years. Some planets might have oceans deeper than Earth's. Some might have continents larger than Earth's. Some might have rings like Saturn, or dozens of moons, or intense magnetic fields that create auroras visible from space. And on some of these worlds there might be life, simple microbes or complex ecosystems, forests, oceans, deserts, perhaps even intelligent beings, looking up at their own night sky, wondering if they are alone in the universe just as we do. The planets of the Milky Way are another dimension of the galaxy's scale. Not just stars, but worlds. Not just points of light, but places. Each one unique. Each one a potential stage for the drama of life and evolution. The galaxy is not just a collection of stars. It is a collection of worlds, a vast multiplicity of places. Each one different, each one real, each one existing right now, orbiting their stars, spinning through space, warmed by their suns. And we have only just begun to explore this cosmic diversity. Of the hundreds of billions of planets in the galaxy, we have studied only a few thousand in any detail. The rest remain unknown, waiting to be discovered, waiting to reveal their secrets. The planets of the Milky Way are a reminder that the galaxy is not empty, not sterile, not lifeless. It is filled with worlds, filled with possibilities, filled with opportunities for complexity and perhaps for life. And the sheer number of these worlds, hundreds of billions or trillions, is another measure of the true scale of the Milky Way. Chapter 14. The Distance to Andromeda, 159-171. We have explored the scale of the Milky Way itself, measuring its size in light years, its mass in solar masses, its population in billions of stars and trillions of planets. But to truly appreciate the scale of our galaxy, we must also consider its place in the larger universe. And the first step in understanding that context is to look at our nearest large galactic neighbour, the Andromeda Galaxy. The Andromeda Galaxy, also known as M31, is the nearest large spiral galaxy to the Milky Way. It is visible to the naked eye from dark locations in the northern hemisphere, appearing as a faint fuzzy patch of light in the constellation Andromeda. To ancient observers, it looked like a small cloud, and it was catalogued as a nebula for centuries before astronomers realised it was actually a galaxy, a separate island of stars far beyond the Milky Way. The distance to Andromeda is about 2.5 million light-years. Let us pause and consider this number, 2.5 million light-years. This is 25 times the diameter of the Milky Way. If the Milky Way is 100,000 light-years across, the distance to Andromeda is 2.5 million light-years. The gap between the galaxies is 25 times larger than the galaxies themselves. 2.5 million light-years is about 24 quintillion kilometers. Light, traveling at 300,000 kilometers per second, takes 2.5 million years to cross this distance. When we look at Andromeda tonight, we are seeing it as it was 2.5 million years ago, long before modern humans evolved. 2.5 million years ago, the Earth was in the Pliocene epoch. Early hominids, our distant ancestors, were just beginning to walk upright on the African savanna. The light we see from Andromeda tonight left that galaxy when these early humans were taking their first steps. If an astronomer in the Andromeda galaxy were observing the Milky Way right now, they would be seeing our galaxy as it was 2.5 million years ago. They would not see human civilization. They would not see cities or spacecraft or radio signals, because those things did not exist yet. They would see a galaxy much like ours, filled with stars and gas, but with no signs of technological intelligence. The distance to Andromeda is so great that even travelling at the speed of light, a journey from the Milky Way to Andromeda would take 2.5 million years. With current spacecraft technology, travelling at 17 kilometers per second like Voyager 1, the journey would take about 44 billion years, more than 3 times the current age of the universe. Even with advanced propulsion systems, travelling at 10% of the speed of light, the journey would take 25 million years. This is longer than the entire history of the hominid family, from the earliest ancestors of humans to the present day. Andromeda is not just far away, it is almost unimaginably far away, separated from the Milky Way by a gulf of empty space so vast that crossing it is beyond any reasonable technological horizon. And yet, Andromeda and the Milky Way are approaching each other. They are being pulled together by their mutual gravity, and in about 4 billion years they will collide. The distance between them, 2.5 million light-years, is closing at a rate of about 110 kilometers per second. This might sound fast, but on cosmic scales, it is slow. At this rate, the distance decreases by about 3.5 light-years per million years. The galaxies are approaching each other, but the collision is still billions of years away. When the collision happens, it will be one of the most dramatic events in the history of the local group. The two galaxies will pass through each other, their gravity pulling and distorting them into long tidal tails. Stars will be flung out into intergalactic space. Gas clouds will collide, triggering enormous bursts of star formation. The supermassive black holes at the centres of both galaxies will eventually merge, creating a single, even more massive black hole. But individual stars will not collide. The distances between stars are so great that the chances of two stars actually hitting each other are vanishingly small. The collision will be a gravitational interaction, not a physical crash. After several billion years, the two galaxies will merge completely, forming a new, larger galaxy. This merged galaxy, sometimes called Milkomeda, will be an elliptical galaxy, a smooth, featureless collection of stars with no spiral arms and no active star formation. It will be the dominant galaxy in the local group, containing the combined mass of the Milky Way and Andromeda, about 2.5 to 3 trillion solar masses. The distance to Andromeda, 2.5 million light-years, is a reminder that the Milky Way is not alone in the universe. It is part of a larger structure called the local group, a collection of more than 50 galaxies bound together by gravity. The Milky Way and Andromeda are the two largest members of the local group, with all the other galaxies being much smaller dwarf galaxies. The local group itself has a diameter of about 10 million light-years. This is 4 times the distance from the Milky Way to Andromeda. The local group contains not just the Milky Way and Andromeda, but also the Triangulum galaxy, the third largest member, and dozens of smaller dwarf galaxies, each one a collection of millions or billions of stars. Beyond the local group lie other groups and clusters of galaxies, separated by tens or hundreds of millions of light-years. The nearest large cluster, the Virgo cluster, is about 53 million light-years away. It contains more than 1,000 galaxies, ranging from small dwarfs to giant ellipticals. The Virgo cluster is part of an even larger structure called the Virgo supercluster, a vast web of galaxy clusters spanning more than 100 million light-years. The Milky Way, vast as it is just one galaxy among hundreds of billions in the observable universe. The distance to Andromeda, 2.5 million light-years, is a small step in the cosmic distance ladder. Beyond Andromeda lie countless other galaxies, each one separated from its neighbours by millions of light-years, each one a collection of billions or trillions of stars, each one a vast cosmic structure in its own right. The distance to Andromeda helps us understand the scale of intergalactic space. The Milky Way is 100,000 light-years across. The distance to Andromeda is 2.5 million light-years. This means that the space between galaxies is about 25 times larger than the galaxies themselves. The universe is not crowded with galaxies. It is mostly empty space, with galaxies scattered like islands in a vast cosmic ocean. This is the context in which the Milky Way exists. It is not isolated. It is part of a larger cosmic community, interacting with neighbouring galaxies through gravity, destined to merge with Andromeda in the distant future. And beyond this local neighbourhood lie countless other galaxies, each one separated by millions or billions of light-years, each one a reminder that the universe is vast beyond comprehension. The distance to Andromeda, 2.5 million light-years, is another measure of cosmic scale. It tells us that the Milky Way, as large as it is just one small part of a much larger universe. And it reminds us that our galaxy, our home, is embedded in a cosmos that extends far beyond our ability to fully comprehend. We have measured the Milky Way in space, its diameter, its thickness, its mass, its population of stars and planets. But there is another dimension to consider: time. The Milky Way is not just big in space, it is also old in time, and understanding its age is essential to understanding its true scale. The Milky Way is approximately 13.6 billion years old. This age is close to the age of the universe itself, which is about 13.8 billion years. The Milky Way formed only about 200 million years after the Big Bang, in the first fraction of the universe's history. 13.6 billion years. This is an almost incomprehensible span of time. Let us try to put it in perspective. Modern humans, Homo sapiens, have existed for about 300,000 years. Recorded human history spans about 5,000 years. The entire history of human civilization, from the first cities to the present day, is only about 10,000 years. The Milky Way is 13.6 billion years old. This is more than 1 million times longer than recorded human history. It is more than 45,000 times longer than the entire existence of modern humans. It is thousands of times longer than the history of life on Earth. If we compressed the entire history of the Milky Way into a single year, with the galaxy forming on January 1st, the Sun would not form until late August. The Earth would form in early September. The first life on Earth would appear in mid-September. Dinosaurs would appear in mid-December. And all of human history, from the first cities to the present day, would occur in the last few seconds before midnight on December 31st. The Milky Way is ancient. It is older than the Sun, older than the Earth, older than life, older than anything we can directly observe on our planet. It has existed for almost the entire history of the universe. The galaxy formed from a vast cloud of gas in the early universe. This gas was mostly hydrogen and helium, the two simplest elements created in the Big Bang. There were no heavy elements, no carbon or oxygen or iron, because those elements are created inside stars, and no stars had yet lived and died to produce them. The first stars in the Milky Way, called Population 3 stars, formed from this primordial gas. They were massive, hundreds of times more massive than the Sun, and they lived fast and died violently, exploding as supernovae after only a few million years. These first supernovae enrich the gas with heavy elements, making it possible for the next generation of stars to form planets, and eventually life. Over billions of years, the Milky Way grew. It consumed smaller galaxies, adding their stars to its own. It formed new stars from the gas in its disk. It evolved from a chaotic, irregular collection of stars into the majestic spiral structure we see today. The disk of the Milky Way is younger than the halo. The halo formed first, about 13.6 billion years ago, when the galaxy was young and irregular. The disk formed later, about 10 to 12 billion years ago. As gas settled into a rotating plane and began forming stars more efficiently, the Sun formed about 4.6 billion years ago, when the galaxy was already 9 billion years old. By the time the Sun was born, the Milky Way was already mature, with well-defined spiral arms and a thick disk of stars. The Sun is a relative newcomer, a middle-aged star in a galaxy that has seen countless generations of stars come and go. The age of the Milky Way also tells us something about the future. The galaxy is now 13.6 billion years old, but it will continue to exist for trillions of years into the future. In about 4 billion years, it will merge with Andromeda, but the merged galaxy, Milkomeda, will continue to exist and evolve. Star formation in the Milky Way has been slowing over time. In the early universe, when gas was abundant, the galaxy formed stars rapidly. But over billions of years, much of the gas has been consumed or blown out of the galaxy. The rate of star formation today is only about 1 to 3 stars per year, much slower than in the past. Eventually, in tens of billions of years, the gas will run out entirely, and star formation will cease. The galaxy will become a collection of old, dying stars, slowly fading as they exhaust their fuel. Red dwarfs, the smallest and longest-lived stars, will continue to shine for trillions of years, but eventually they too will fade. In the very distant future, perhaps 100 trillion years from now, the last stars in the galaxy will die, and the Milky Way will become a dark, cold collection of stellar remnants, white dwarfs, neutron stars, and black holes. It will be a galaxy in name only, a ghost of its former self, invisible except through its gravitational effects. But even this is not the end. Over unimaginably long timescales, trillions upon trillions of years, even the stellar remnants will decay or evaporate. White dwarfs will cool to black dwarfs, cold and inert. Black holes will slowly evaporate through Hawking radiation, and eventually, on timescales so long they are almost meaningless, the galaxy will dissipate entirely, its matter spread across the ever-expanding universe. But this is so far in the future that it is almost irrelevant. For the foreseeable future, for billions or even trillions of years, the Milky Way will continue to exist, to form stars, to evolve, to be a home for countless worlds and perhaps countless forms of life. The age of the Milky Way, 13.6 billion years, is another measure of its scale. Not just how big it is in space, but how long it has existed in time. The galaxy is ancient, a structure that has endured for almost the entire history of the universe, and that will endure for trillions of years into the future. When we look at the Milky Way, we are not just seeing a structure in space, we are seeing a structure in time, a galaxy with a history stretching back to the cosmic dawn, and a future extending far beyond our ability to imagine. The Milky Way is not just vast, it is also eternal, at least on human timescales. It was here long before us, and it will be here long after we're gone. It is a structure that transcends individual lives, individual civilizations, perhaps even individual species. It is a cosmic monument, a testament to the enduring nature of the universe. We have explored the Milky Way in great detail, measuring its size, mass, population, and age. But to truly appreciate its scale, we must also compare it to other galaxies. How does the Milky Way stack up against the other galaxies in the universe? The Milky Way is a large spiral galaxy. It is not the largest galaxy known, but it is far from the smallest. It is a heavyweight in the cosmic arena, a respectable member of the galactic community. The Milky Way has a diameter of about 100,000 light-years and a mass of about 1 to 1.5 trillion solar masses. It contains about 300 billion stars. These are the numbers we have been exploring throughout this journey, but how do these numbers compare to other galaxies? The nearest large spiral galaxy, Andromeda, is slightly larger than the Milky Way. Andromeda has a diameter of about 220,000 light-years, more than twice the diameter of the Milky Way. Its mass is estimated at about 1.5 trillion solar masses, slightly more than the Milky Way, and it contains about 1 trillion stars, more than 3 times as many as the Milky Way. Andromeda is bigger, more massive, and more populous than the Milky Way. It is the dominant galaxy in the local group, and when the two galaxies eventually merge, Andromeda's slightly larger mass will make it the dominant partner in the merger. But even Andromeda is not particularly large by cosmic standards. There are spiral galaxies much larger than either the Milky Way or Andromeda. NGC 6872, a spiral galaxy about 200 million light-years away, has a diameter of about 500,000 light-years, 5 times the diameter of the Milky Way. It is one of the largest spiral galaxies known, its arms stretched and distorted by a collision with a smaller galaxy. Malin 1, an enormous low-surface brightness galaxy, has a diameter of about 650,000 light-years, more than 6 times the diameter of the Milky Way. It is so diffuse that it was not discovered until 1986, despite being relatively nearby in cosmic terms. But the largest galaxies are not spirals. They are elliptical galaxies, vast collections of old stars with no spiral arms and no active star formation. IC 1101, one of the largest galaxies known, is a giant elliptical galaxy at the center of a galaxy cluster, about 1 billion light-years away. It has a diameter of about 6 million light-years, 60 times the diameter of the Milky Way. It contains about 100 trillion stars, more than 300 times the population of the Milky Way. Its mass is estimated at about 100 trillion solar masses, 100 times the mass of the Milky Way. IC 1101 is a monster, a galaxy so large that it dwarfs the Milky Way. If IC 1101 were placed at the center of the local group, its outer edges would reach past Andromeda and encompass most of the known galaxies in the group. These giant elliptical galaxies are rare. Most galaxies are much smaller than the Milky Way. Dwarf galaxies, with masses of only a few million to a few billion solar masses, are the most common type of galaxy in the universe. The Large Magellanic Cloud, a satellite of the Milky Way, is a dwarf irregular galaxy with a mass of about 10 billion solar masses and a diameter of about 14,000 light-years. It is only about 10% the diameter of the Milky Way and contains only about 3% as much mass. Even smaller are the ultra-faint dwarf galaxies, some of which contain only a few thousand stars. These galaxies are so faint that they are almost impossible to detect, and many of them probably remain undiscovered. The Segway 2 dwarf galaxy, one of the smallest known galaxies, contains only about 1,000 stars and has a mass of only about 500,000 solar masses. It is more like a large star cluster than a true galaxy, but it is held together by dark matter, which makes it technically a galaxy. The Milky Way, with its 300 billion stars and trillion solar mass halo, is a giant compared to these ultra-faint dwarfs. But it is average or even small compared to the largest galaxies in the universe. This range of sizes is one of the remarkable features of galaxies. They come in an enormous variety, from tiny dwarfs with only a few thousand stars to giant ellipticals with trillions of stars. The Milky Way sits somewhere in the middle of this range, neither the largest nor the smallest, but a respectable, well-populated galaxy. In the context of the observable universe, with its estimated 2 trillion galaxies, the Milky Way is unremarkable. There are many galaxies similar to it, and many that are larger or smaller. But to us, the Milky Way is special. It is our home, the only galaxy we can study in detail, the only galaxy where we can see individual stars and map structures with precision. Comparing the Milky Way to other galaxies gives us perspective. It reminds us that our galaxy, vast as it is just one among countless others, and it reminds us that the universe is filled with structure on every scale, from the smallest dwarf galaxies to the largest ellipticals, each one a collection of stars and gas and dark matter, each one a cosmic structure in its own right. The Milky Way is big, but in the context of the universe, it is just average. And this, perhaps, is the most humbling realization of all. We have journeyed through the Milky Way, measuring its size, mass, and population. We have compared it to other galaxies and placed it in the context of the local group. But to truly appreciate the scale of the Milky Way, we must also consider its place in the largest structure of all, the observable universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It is not the entire universe, which may be infinite, but it is the part of the universe we can observe, the part that is accessible to our telescopes and instruments. The observable universe has a diameter of about 93 billion light-years. This is almost incomprehensibly large. It is 930 times the diameter of the Milky Way. If the Milky Way were the size of a coin, the observable universe would be a sphere more than 9 meters across. 93 billion light-years. Light, travelling at 300,000 kilometers per second, would take 93 billion years to cross the observable universe. But the universe is only 13.8 billion years old. How can the observable universe be 93 billion light-years across if the universe is only 13.8 billion years old? The answer is expansion. The universe is expanding, and it has been expanding since the Big Bang. As the universe expands, space itself stretches, carrying galaxies away from each other. The most distant objects we can observe are now about 46.5 billion light-years away, even though the light from them has been travelling for only 13.8 billion years. This expansion means that the observable universe is much larger than we might naively expect, and it is growing larger all the time as light from more distant regions reaches us. Within the observable universe, there are an estimated 2 trillion galaxies. 2 trillion. This is more than 6 times the number of stars in the Milky Way. If each galaxy contains on average 100 billion stars, then the observable universe contains about 200 billion trillion stars. This is written as 2 times 10 to the 23rd, a number with 24 digits. 200 billion trillion stars. This is more stars than there are grains of sand on all the beaches on Earth. It is more stars than the number of cells in all the humans who have ever lived. It is an incomprehensibly large number, and the Milky Way is just one of those 2 trillion galaxies. One galaxy among an almost infinite multitude. Our 300 billion stars are a tiny fraction of the total stellar population of the observable universe. This puts the scale of the Milky Way in perspective. The galaxy is vast, containing hundreds of billions of stars spread across 100,000 light-years. But in the context of the observable universe, it is infinitesimally small. The Milky Way occupies about 1 part in a billion of the volume of the observable universe. It is a tiny speck in a vast cosmic ocean, and yet the Milky Way is all we have. It is our cosmic home, the only galaxy we can study in detail, the only galaxy where we can see individual stars and planets, the only galaxy where we know for certain that life exists. The observable universe is not uniform. Galaxies are not randomly scattered through space. They are organized into structures, groups, clusters, superclusters, and even larger structures called filaments and walls. The Milky Way is part of the local group, which is part of the Virgo supercluster, which is part of an even larger structure called the Laniakea supercluster. Laniakea contains about 100,000 galaxies spread across 520 million light-years. It is our cosmic address on the larger scales. But even Laniakea is just one of many superclusters in the observable universe. There are an estimated 10 million superclusters, each containing tens of thousands to hundreds of thousands of galaxies. The large-scale structure of the universe is sometimes called the cosmic web. It consists of vast filaments of galaxies stretching across hundreds of millions of light years, surrounding enormous voids where few galaxies are found. The filaments intersect at nodes, where galaxy clusters and superclusters form. The whole structure looks like a vast three-dimensional spiderweb, with matter concentrated along the threads and emptiness filling the spaces between. The Milky Way is located on one of these filaments, part of the Laniakea supercluster, moving through space along with hundreds of billions of other galaxies, all of them being carried by the expansion of the universe. On the larger scales, the universe is remarkably uniform. If you look at a region of space several 100 million light-years across, it looks much the same as any other region of the same size. Galaxies, clusters, and voids are distributed in roughly the same way everywhere. This uniformity is evidence that the universe began in a hot, dense, uniform state, and that the structures we see today grew from tiny density fluctuations in the early universe. The observable universe is the larger structure we can meaningfully study. Beyond the edge of the observable universe, there is more universe, perhaps infinitely more, but it is forever beyond our reach. The light from those regions has not yet had time to reach us, and because the universe is expanding, it never will. The Milky Way, vast as it is just one tiny part of this incomprehensibly large cosmos, and yet it is our part. It is home. It is the galaxy where we were born, where our sun shines, where our planet orbits, where life arose and evolved and eventually produced beings capable of looking up at the night sky and wondering about their place in the universe. The scale of the observable universe, 93 billion light-years across, containing 2 trillion galaxies and 200 billion trillion stars, is the ultimate context for understanding the Milky Way. Our galaxy is vast, but it is also infinitesimal. It is everything to us, and nothing in the grand scheme of the cosmos. And this duality, this tension between the personal and the cosmic, is at the heart of our quest to understand the true scale of the Milky Way. Throughout this journey, we have been dealing with numbers that are almost impossible to comprehend. Light years, trillions of kilometers, billions of stars, trillions of solar masses. These numbers are so large that they lose meaning. Our brains did not evolve to visualize such scales. We are creatures of the human world, comfortable with meters and kilometers, hours and days, but not with light years and billions of years. So let us try a different approach. Let us try to visualize the scale of the Milky Way using analogies and comparisons, bringing the incomprehensible down to a level we can grasp. Imagine the sun as a grain of sand, about 1 millimeter across. On this scale, the Earth would be a speck of dust, much too small to see, orbiting about 10 centimeters from the sun. Jupiter would be orbiting about half a meter away. The edge of the solar system, the orbit of Neptune, would be about 3 meters away. On this scale, where the sun is a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand about 30 kilometers away. 30 kilometers. That is the distance between neighbouring stars when the stars themselves are reduced to grains of sand. The Galactic Center, 26,000 light-years away, would be about 190,000 kilometers distant. That is about half the distance from the Earth to the Moon. The far edge of the galaxy would be about 700,000 kilometers away, nearly twice the distance from the Earth to the Moon. On this scale, the entire Milky Way, 100,000 light-years across, would be about the size of the inner solar system in real life, extending past the orbit of Mars. But instead of a few planets, it would contain 300 billion grains of sand, each one a star, spread throughout this vast space. This analogy helps us visualize the emptiness of the galaxy. Even with 300 billion stars, the galaxy is mostly empty space. The distances between stars are enormous compared to the sizes of the stars themselves. Let us try another analogy. Imagine the Milky Way as a city, a vast metropolis of stars. The Galactic Center is downtown, a dense cluster of skyscrapers and bright lights, bustling with activity. The spiral arms are the main streets, lined with new buildings and construction sites, representing the regions of active star formation. Our sun is located in the suburbs, about halfway from downtown to the city limits. The neighbourhood is quiet, not too crowded, not too sparse. The nearest neighbours are a few blocks away. The city limits, the edge of the galaxy, are about the same distance from downtown as we are, but in the opposite direction. Beyond the city limits lies the halo, a vast rural area surrounding the city, sparsely populated with old farmhouses and small towns, representing the old halo stars and globular clusters. And beyond the halo lies the countryside, intergalactic space, largely empty but with other cities, galaxies, visible in the distance. On this analogy, the distance to Andromeda, 2.5 million light-years, would be like the distance to another city about 25 city widths away. Far, but not inconceivably far. You could not walk there, but you could imagine the journey. Another way to visualize the scale is through time. We have said that light takes 100,000 years to cross the galaxy. Let us imagine a journey at the speed of light, and let us compress that journey into a more manageable timescale. Suppose we compress the 100,000-year journey into 1 year. On this timescale, travelling at the speed of light feels like travelling 100,000 times faster than light actually travels. We cross the galaxy in 1 year instead of 100,000 years. Starting from the edge of the galaxy on January 1st, we would pass through the outer disk, seeing sparse populations of old stars and diffuse gas. By mid-January, we would enter a spiral arm, seeing bright young stars and glowing nebulae. By early February, we would be in the interarm region, a quieter area with older stars. We would pass through several spiral arms over the next few months, each one marked by an increase in star density and brightness. By mid-year, around July, we would be approaching the Galactic Center. The density of stars would increase dramatically, and the sky would be filled with millions of bright stars. By late July, we would reach the Galactic Center itself, the supermassive black hole and the dense star cluster surrounding it. We would spend only a few days in this region, then continue on to the other side of the galaxy. By December, we would be approaching the far edge, leaving the disk and entering the sparse outer halo. On December 31st, 1 year after we started, we would exit the Milky Way and enter intergalactic space. This time, compression helps us appreciate the journey, even though it does not reduce the actual distances involved. 100,000 light-years is still 100,000 light-years, but by compressing it into 1 year, we can imagine the progression, the passage through different regions, the changing density and character of the galaxy. No matter how we try to visualize it, the scale of the Milky Way remains almost incomprehensible. 100,000 light-years across, 300 billion stars, 1 trillion solar masses. These numbers are so large that they defy our intuition, our ability to picture them in our minds. But perhaps this is appropriate. Perhaps the Milky Way should be incomprehensible. Perhaps its scale should inspire awe and humility, rather than easy understanding. Perhaps the fact that we can measure it, even if we cannot fully visualize it, is itself a testament to human ingenuity and curiosity. We are tiny beings on a small planet orbiting an ordinary star in an average location in a large but not extraordinary galaxy. And yet, we have measured that galaxy. We have mapped its structure, counted its stars, weighed its mass, determined its age. We have placed it in the context of the universe and understood its role in the cosmic web. This is the achievement of astronomy. Not just to measure the scale of the Milky Way, but to make it comprehensible, to bring the incomprehensible within the reach of human understanding, even if only in an abstract mathematical way. The Milky Way is bigger than we can imagine, but it is not bigger than we can understand. We have explored the Milky Way in great detail, measuring its size and mass, counting its stars and planets, comparing it to other galaxies and placing it in the context of the universe. Now let us bring the focus back to ourselves. What is our place in this vast structure? What is our cosmic address? Our most specific address is Earth, the third planet from the Sun, orbiting at an average distance of about 150 million kilometers. Earth is a small rocky world, about 12,700 kilometers in diameter, with a thin atmosphere and abundant liquid water on its surface. It is the only place in the universe where we know for certain that life exists. Earth orbits the Sun, a yellow dwarf star of spectral type G2V, with a mass of about 2 × 10 to the 30th kilograms, or about 330,000 times the mass of Earth. The Sun is about 4.6 billion years old, roughly halfway through its main sequence lifetime. It is an ordinary star, one of about 300 billion in the Milky Way. The Sun is located in the Orion Spur, a minor spiral arm that branches off from the Sagittarius arm. We are about 26,000 light-years from the Galactic Center, roughly halfway from the center to the edge of the disk. We are about 70 light-years above the galactic plane, moving upward in a slow oscillation that will carry us to a maximum height of about 250 light-years above the plane before we fall back down. The Orion Spur is a relatively quiet region of the galaxy. We are between the major spiral arms, away from the most intense star formation and the highest risk of nearby supernovae. This may have been beneficial for the development of life on Earth, providing a stable environment over billions of years. Our neighbourhood contains several dozen stars within 10 light-years. The nearest star is Proxima Centauri, a red dwarf 4.24 light-years away. Within 100 light-years, there are about 14,000 stars, most of them red dwarfs, with a scattering of sun-like stars and a few massive stars. We orbit the Galactic Center at a speed of about 230 kilometers per second. At this speed, it takes us about 230 million years to complete one orbit. Since the Sun formed about 4.6 billion years ago, we have completed only about 20 orbits around the galaxy. 20 laps around the galactic racetrack in the entire history of the Sun. Our larger address is the Milky Way galaxy, a barred spiral galaxy with a diameter of about 100,000 light-years and a mass of about 1 trillion solar masses. The Milky Way contains about 300 billion stars, at least 300 billion planets, vast clouds of gas and dust, a supermassive black hole at its center, and a dark matter halo that extends far beyond the visible galaxy. The Milky Way is part of the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group has a diameter of about 10 million light-years. The two largest members are the Milky Way and the Andromeda Galaxy, with all other members being much smaller dwarf galaxies. The Local Group is gravitationally bound, meaning all its members are held together by their mutual gravity and will not be carried apart by the expansion of the universe. The Local Group is part of the Virgo supercluster, a larger structure containing about 100 groups and clusters of galaxies, spread across about 110 million light-years. The Virgo supercluster contains about 47,000 galaxies, with a total mass of about 1 quadrillion solar masses. But even the Virgo supercluster is not the largest structure we are part of. It is a small lobe of an even larger structure called the Laniakea supercluster. Laniakea contains about 100,000 galaxies spread across 520 million light-years. Its name means immense heaven in Hawaiian, a fitting name for such a vast structure. Laniakea is defined not by the positions of galaxies, but by their motions. All the galaxies in Laniakea are flowing toward a common gravitational center called the Great Attractor, a region of space with an unusually high concentration of mass. The Milky Way is moving toward the Great Attractor at about 600 kilometers per second, carried along by the gravitational pull of this massive structure. Beyond Laniakea, our address becomes less specific. We are part of the observable universe, a sphere about 93 billion light-years in diameter, containing about 2 trillion galaxies. And beyond the observable universe, there is more universe, perhaps infinitely more, but it is forever beyond our reach. Our cosmic address, then, is Earth Solar System, Orion Spur, Milky Way, Galaxy, Local Group Virgo, Supercluster, Laniakea, Supercluster, Observable Universe. Each level of this address is vastly larger than the one before. The jump from Earth to the solar system is a factor of about 10 billion. The jump from the solar system to the Milky Way is a factor of about 10 billion again, and the jump from the Milky Way to the observable universe is another factor of about 1 billion. Our cosmic address is a reminder of our place in the universe. We're on a small planet orbiting an ordinary star in a typical location in an average galaxy, in a small group, in a modest supercluster in a vast universe. We're insignificant on cosmic scales. The universe does not care about us. It does not know we exist. We're a tiny, temporary phenomenon, a brief flicker of consciousness in a cosmos that is vast, ancient, and indifferent. And yet, we are also significant. We are the only beings we know of who can understand the universe, who can measure its scale, who can contemplate their place within it. We are the universe become conscious of itself, matter organized in such a way that it can think and wonder and create. Our cosmic address is both humbling and empowering. It tells us how small we are, but also how remarkable. We are tiny, but we are part of something vast. We are brief, but we are part of something ancient. We are isolated, but we are connected to everything around us through the history of the cosmos. The Milky Way is our home on the largest scales, Earth is our home on the smallest, and between them lie all the layers of our cosmic address, each one a reminder of the structure and scale of the universe and of our place within it. Chapter 20. The Wonder of Scale. 231, 243. We have journeyed through the Milky Way, from the nearest stars to the far edge, from the galactic center to the halo, from the disk to the dark matter, from individual planets to the observable universe. We have measured distances in light years, masses in solar masses, populations in billions and trillions. We have explored structures so vast that light takes hundreds of thousands of years to cross them. And now, as our journey comes to an end, let us reflect on what all of this means. What is the significance of the scale of the Milky Way? Why should we care that the galaxy is 100,000 light-years across, that it contains 300 billion stars, that it weighs 1 trillion solar masses? The scale of the Milky Way is significant first and foremost because it is a measure of the universe we live in. The galaxy is our cosmic home, and understanding its scale helps us understand our place in the cosmos. It reminds us that we are part of something vastly larger than ourselves, something that existed long before us and will continue long after we're gone. The scale of the Milky Way also reminds us of the limits of human experience. We are creatures adapted to life on the surface of a small planet. Our senses, our intuitions, our mental models of the world are all calibrated to this scale. We understand distances of meters and kilometers, times of seconds and hours, masses of kilograms and tons. But the scale of the galaxy is so far beyond this that it defies our intuition. Light years, billions of stars, trillions of solar masses, these are not things we can experience directly. We can only understand them abstractly, through mathematics and analogy, through patient observation and careful reasoning. And yet, we do understand them. This is one of the great achievements of human civilization. We have extended our understanding beyond the limits of our direct experience. We have measured the unmeasurable, visualized the unvisualizable, comprehended the incomprehensible. The scale of the Milky Way is also a reminder of the richness and diversity of the universe. The galaxy contains hundreds of billions of stars, each one unique, each one with its own history. Many of these stars have planets, and some of those planets might have life. The galaxy is not empty or barren, it is filled with worlds, filled with possibilities, filled with opportunities for complexity and perhaps for consciousness. We do not know how common life is in the galaxy. We have only one example, Earth. But the sheer number of stars and planets suggests that the opportunities for life are vast. If even a tiny fraction of those opportunities result in actual living worlds, the galaxy could be teeming with life, and some of that life might be intelligent. Some of it might have developed technology, might have built civilizations, might be looking up at their own night sky and wondering if they are alone in the universe, just as we do. The scale of the Milky Way is a measure of the arena in which this cosmic drama unfolds. It tells us how much space there is for life to arise, how many stars and planets there are to explore, how vast the stage is on which the story of the universe is being told. The scale of the Milky Way is also humbling. When we contemplate the vastness of the galaxy, the billions of stars and trillions of planets, the hundreds of thousands of light years and billions of years, we cannot help but feel small. We are reminded that we are not the center of the universe, that the cosmos does not revolve around us, that we are a tiny temporary phenomenon in a universe that is vast, ancient and enduring. This humility is valuable. It reminds us that our concerns, our conflicts, our ambitions, though they may seem all important to us, are insignificant on cosmic scales. The universe does not care about our politics, our economies, our wars. It continues on, indifferent to our struggles. But this humility should not lead to despair. Yes, we are small. Yes, we are temporary, but we are also remarkable. We are the only beings we know of who can understand the universe. We are matter that has become conscious, that can think and reason and create. We are the universe's way of knowing itself. The scale of the Milky Way is a measure of the mystery that surrounds us. For all that we have learned, for all that we have measured and mapped, there is still so much we do not know. We do not know what dark matter is. We do not know if there is life elsewhere in the galaxy. We do not know the full history of the Milky Way's formation and evolution. We do not know what the future holds, beyond the broad outlines of galactic mergers and stellar evolution. The galaxy is still full of secrets, still full of mysteries waiting to be solved. And this is as it should be. The quest to understand the universe is endless. Each answer leads to new questions. Each discovery reveals new layers of complexity. The scale of the Milky Way, 100,000 light-years across, 300 billion stars, 1 trillion solar masses, 13.6 billion years old, is not just a collection of numbers. It is a testament to the grandeur of the universe, to the richness of the cosmos, to the endless capacity of nature to surprise and amaze us. It is a reminder that we live in a universe of wonders, a cosmos filled with structures and phenomena that challenge our understanding and inspire our imagination. And it is an invitation to keep exploring, to keep questioning, to keep seeking to understand the true scale of the universe and our place within it. The Milky Way is big, bigger than we can imagine, but not bigger than we can understand, and in that understanding we find both humility and wonder, both our insignificance and our significance, both the limits of our existence and the limitless reach of our curiosity. As we conclude our journey through the true scale of the Milky Way, we're left with a sense of awe and wonder. The galaxy is vast beyond comprehension, a structure of such enormous size and complexity that it defies our everyday intuition. 100,000 light-years from edge to edge, 300 billion stars scattered throughout the disk and halo, at least 300 billion planets, perhaps a trillion, 1 trillion solar masses, most of it in the form of invisible dark matter, 13.6 billion years of history, stretching back to the first fraction of the universe's existence. These are the measurements of the Milky Way, the numbers that define its scale. But the true scale of the galaxy is more than just numbers. It is the realization that we are part of something vastly larger than ourselves. It is the understanding that our galaxy is one among trillions in the observable universe, and that each of those galaxies is itself a vast collection of stars and worlds. The scale of the Milky Way challenges us to expand our perspective, to think beyond our immediate surroundings, to contemplate the cosmos in all its grandeur. It reminds us that we are citizens not just of Earth, not just of the solar system, but of the galaxy itself. And it reminds us that the universe is bigger than we think, always bigger. Every time we push the boundaries of our knowledge, we discover that there is more beyond, more distance, more time, more stars, more galaxies, more mystery. The Milky Way is our home on the grandest scales. It is the galaxy where we were born, where our sun shines, where our planet orbits in a quiet corner of a minor spiral arm. It is the galaxy we can study in detail, the only galaxy where we can see individual stars and planets, the only galaxy where we know for certain that life exists, and it is vast, bigger than you think, bigger than you can imagine, a cosmic structure of such immense scale that it takes light 100,000 years to cross it, a collection of hundreds of billions of suns spread across a distance so great that the mind cannot hold it all at once. Thank you for joining us on this journey through the true scale of the Milky Way. May you rest well under the stars, knowing that you are part of something magnificent, something ancient, something vast beyond measure. May your dreams carry you across the 100,000 light years of our galactic home, from the nearest stars to the far edge, from the disk to the halo, from the visible matter to the dark matter that holds it all together. Clear skies, and may you always remember how big the galaxy really is.